In section 15.3, we're going to learn about partial derivatives. Now we know from Calculus 1 that derivatives represent the slope of a tangent line to a curve. But what does this mean for our multivariable functions where your graphs are surfaces, not curves? How is this going to work? And the answer is that we treat one of the variables as if it's a constant, and we take the derivative with respect to the other variable. So suppose we have a function z equals f of xy, which is the surface right here. And we want to take the partial derivatives. Well, there's two potential partial derivatives for z equals f of xy. We could take the derivative of that z function with respect to x, and we abbreviated this. These are delta signs, so lowercase delta. So delta z, delta x, or f with a little subscript after it for x. That would be the slope of the tangent line to the curve if you cut across it. So you fix your y value. You imagine your y value is fixed. So you're cutting across your surface with a plane. And when you do that, when you hack into that surface with that plane, if you fix your y, then you're going to have this curve. And the partial derivative would be the slope of that curve. So the tangent, slope of the tangent to that curve would be delta z over delta x at the point A, B. In other words, it's f subscript x. So you're taking the partial derivative of the function f with respect to x at the point AB. That would be your slope. And you're setting y constant. That's what this plane stands for. So this plane means you're going to set y is equal to b, which is a constant. Similarly, you can do the same thing with respect to y. So that would be setting x as constant. You can see you're going to cut into your surface with a constant x, so it's a plane, right? But it's a plane that intersects the x-axis instead of the y-axis. And so then you'd have, wherever that point is, there would be a tangent line. So when you cut into it, that creates a curve, right? You cut into your surface, hack it into it with a plane, it makes a curve. And then the tangent line to that curve at that point is, or has a slope, I should say, of delta z over delta y. I know they look like 2's, but they're not 2's. They are deltas. I should make the bottom part, the bottom loop a little bit bigger to make it more obvious it's not a 2. Sorry, that's just how I draw them. All right, so delta z over delta y at the point AB, which is f y AB. All right, so let's actually do a couple problems, and I think it'll make more sense when we do them. But that's the graphical theory behind what we're doing. Okay, so the delta z over delta x or delta z over delta y are the rates of change of that z curve, or excuse me, the z surface with respect to x if you're assuming that y was held constant. And similarly for delta z, delta y, the partial derivative of z with respect to y. So let's look at the mechanics of partial derivatives for a minute, and then we'll work on interpretations later. So I'm going to start off with finding the indicated partial derivative. So I want to find f sub x of xy, which is the same thing as delta z over delta x. So I'm going to take the derivative of each of these pieces as if y is constant. So the derivative of 2x to the fourth would be 8x to the third. Y, if it's constant, like 4, then the derivative of that would be 0. Plus, and then again, this is constant. So this is just some number that you're imagining. So it's 5y cubed times 2x. So you treat the 5 and the y cubed as if they're constant, and then take the derivative of the x squared part. So that would mean that the partial derivative is 8x cubed plus 10xy cubed. And there you go. All right, let's do it again, but now for y. So we're going to assume that x is constant. So this is the partial derivative of z with respect to y. Okay, well, the derivative of the first bit, if that's a constant, then the derivative of it is 0. Y squared would be minus 2y plus, now the 5 and the x squared are constant, so just write them, and then take the derivative of the y cubed, so that would be 3y squared. So that would be 15x squared y squared, take away 2y. And there we go. All right, now what if we have 3 dimensions? And the answer is, it's the same thing. So let me find fx of x, y, z, which again is the same thing as, now this would be w here because we have need of z, so your w is this function. So partial derivative of w with respect to x. Okay, so 4x for this bit, leave the y alone, minus, okay, this has no x's in it at all, which means as far as we are concerned, this is a constant, like a number, like 70 or something. So if this is 70, the derivative of it is 0 plus, or excuse me, minus 0 plus another 0, because the derivative of that is also 0, since that whole thing is assumed to be constant. So it'd be 4xy for this. All right, now what about y? The derivative of this function w with respect to y. Okay, on the first bit, this part up here is constant. So I'm just going to write 2x squared, and the derivative of y is 1 minus, all right, this will be 10z squared, because the 10 and the z squared are constant, and then the derivative of the y squared would be 2y, and then the last bit has no y in it, so the derivative of that would be 0. So that means it's 2x squared minus 10, oh no, minus 20. Sorry, there's 2 there. 2 times 10 is 20 yz squared. All right, last one, z. The partial derivative of w with respect to z would be equal to, okay, well, there's no z in the first term at all, so that's 0. The next term has a 10y squared times, and the derivative of z squared is 2z. And then the last one would be 24z squared. So that would be 24z squared, take away 20 y squared z. And there's your partial derivative with respect to z.